Hello, welcome to today's online training, part 6, Introduction to Steel Design for RFEM 6 for students. My name is Andreas Hörold. I'm responsible for marketing and public relations in the company Dlubal Software. I'm responsible, for instance, for the website, German and English webinars, such trainings here, the newsletter, and so on. I've been working for the company Dlubal Software, for Dlubal Software for 12 years now. My colleague Markus will support me, but he can introduce himself.
Hello, my name is Markus Baumgartel. I am responsible for customer support and frequently asked questions on our website. And today I will help my colleague Andreas to answer your question during this training. Okay.
Okay, thank you for your introduction. Then we can switch off our webcams that the attendees can see the full screen. You can ask questions via the control panel that you can see on the right side of your screen. You can show or hide it with that arrow here. Yeah, and then you can enter the question here and Markus will answer you. Okay, then that's our training series. That are the trainings that are already presented, that we presented, my colleagues and so on. And today, that is the last part, Introduction to Steel Design, but you can't find on our website all the recordings of the previous webinars. So to the content today, at first I say something about the theoretical background. Then we start with the first example, a simple two-span beam. I say something about imperfections, linear, geometrical linear analysis or second order theory and so on. Then I say something about the stability proofs in the ultimate limit state design. And we finished the online training with the second example, a flat hall frame. Okay, before I come to the products for design according to Eurocode 3, where I have some question, or I have one question. How much experience do you have in steel design? I start the poll. Just click on the button that is valid to you. I give you some seconds. Now just click on the button professional, or it's new for me, and so on. Okay, then I close the poll. So that's the result. Yeah, I'm professional, 33%, but also 33% said or checked it's new for me. We have from all clicks. Okay, I hope also the professionals will learn something about the steel design today. We will see. Okay, those are the products for design according to Eurocode 3 in RFEM 6. With your student version, there are available all add-ons. Also, you can download these standalone programs such as RSection or RWind. So we start with steel design. That's the main program for steel design. We will use it today. You can design steel members according to international standards, such as Eurocode, AESC, and so on. Then there's torsional warping, where you can consider also the torsional warping in the global server. Then steel joints. Yeah, you can analyze steel joints based on the FE or FEA method. Then the standalone program, R-section, a cross-section program. Then structure stability, where you can do a stability analysis. We will use it in the second example. Then nonlinear material behavior, if you want to consider, for example, plastic material behavior of steel, for example. And the add-on stress-strain analysis. Okay, a little insight into the whole safety concept in steel construction. The actions should always be smaller than the resistance. In addition, we have also certain coefficients that we have to take into account depending on what type of proof is used. For example, for the stability analysis, there's a different safety factor for basic standard and national annex of Germany. Just consider the national annex of your country. But I believe in the most cases it's the standard factor from the Eurocode. Okay, then that's quite important. I will also ask you later I ask you a question in the poll. Elastic or plastic global analysis. Whether an elastic or plastic calculation is possible always depends on the cross-section. There are 4 cross-section classes. Let me introduce them. Cross-section class 1, where is a high rotation capacity. This allows a plastic structure calculation. For example, plastic hinges can be taken into account. Usually you won't do that. It's not so often used in the practice. It's in the cross section, resistance can be applied plastically. It's an economical method, but also somewhat more complex in the calculation when you use the plastic global analysis. But as I said, it's not often used. Just consider the plastic or the cross-sectional resistance, that this can be applied plastically. Then cross-section class 2, where there's a low rotation capacity, and this allows an elastic structural calculation. And as with cross-section class 1, the cross-sectional resistance can also be applied plastically. Cross-section classes 3 and 4 allows an elastic structure analysis, and the cross-section resistance can only be applied elastically. You can consider plastic cross-section resistance for cross-section classes 1 and 2, and only an elastic resistance for cross-section classes 3 and 4. I hope you understood it right. I start the next poll. Just click on the button that you want, or what you think it's the right answer. So I close the poll. Really good. All of you checked the right button or give the right answer. Great. Okay, then we turn to the next slide. Two-span beam. That's the first simple example. It's a two-span beam. The beam is an IPE 550, and I've got 2 load cases. And tasks are cross-section classification, cross-section design checks, difference between elastic and plastic cross-section resistance. Means the design check elastic, and elastic plastic. Okay, let's turn to RFEM 6. I create a new file here, left above, file new. So the model name is two-span beam. I use the 2D model. That's enough for this example. It's only one beam, plane stress. Then I activate the add-on steel design. Standards. Okay, I checked the German National Annex. You can see there are also different standards available for the cross load case classification. I select the Eurocode and the German National Annex. The same for the load wizards, but we don't use any load wizard in this example. Doesn't matter. Then here the different standards, the international standards, as I mentioned. I use the Eurocode and the German National Annex. That's all. Okay. So then I change the work plane or the visibility view in reverse Y direction. Zoom a little bit in. Okay. The grid, we can check the grid. The space is 1 meter. Here at the bottom, grid. I double or open it, the dialog, and the grid of 1 meter is okay. Okay, then left above, new single member. Beam is okay. Then we have to define the cross section. There's already an HEB 300, and we changed it with input from section library. We open the library. Standardized, left above. And I choose, as I mentioned, for example, this one, IPE 550. And I need to select the material. There's already S235 selected, but I open also the library. So European Union is okay, steel, and I choose any steel that I want, or I check on the left side carbon steel and the simple steel S235. Okay, so that's all. So now I create the beam, the whole beam, 24 meters. Okay, and I divide the beam here in the middle with right click on the beam, then members, divide member in intermediate nodes. One node is okay, and that I don't divide the member, or I will only create a node on the member. That's why I check create on member nodes without dividing the member. Okay, that I can apply a support here in the middle. So we start with the first support here, left above, assign nodal support. I click on it and let me check the proposed nodal support. Yeah, that's okay. Translational in longitudinal or in X direction and in Z direction. Okay. This one. Okay, it's very small. That's no problem. I right click on it and increase the size of the support. It's only a display setting. So then the next supports, I define a new support. Should be fixed in Z direction, but not in X direction. Okay. Okay. And I select this node and this node. Okay. We finished the beam. The self-weight load case is already created. I enter a new member load here at the top. New member load. 8 kilonewton per meter in Z direction. Okay. Okay. Yeah, just a hint, if I too quick for you, yeah, we think that it's the best that you only watch the webinar, yeah, without any modeling, and later you can go through the webinar with the recording. We provide the recording, and then you can, yeah, stop the video when you yeah, model not so quickly. And yeah, that's the sense of such online training. Okay, then here above, new load case. And with a click on this button, we turn to the load cases and combinations. I enter the next load case, imposed load. I call it also imposed load. So, okay, action category is okay, name is okay, and I can leave the dialog. Okay. So, and then I enter the next member load. 12 kilonewton per meter in Z direction. Okay. So that's all. We finish the beam and the loads. We turn on the left side in the navigator data. We open the design situations. Now we open the same dialog. Those are the load cases. Those are the base data, the standard group, and the national annex. And we would like to use also the combination wizard. So we have got two actions and those design situation. We would like to do only an ultimate limit state design. That's why I select with the Shift key all the three serviceability limit state design situations and delete them. Okay, the steel design is already checked. That's okay. Then there are action combinations and the load combinations. Only two load combinations. So then I can calculate all. So then let's take a look at the results for the ultimate limit state design. Here on the left side, you can see the two deformations, minimum deformation and maximum deformation. Now we have got two combinations. So, and I can check the envelope values, and I can also display only the maximum values if I want. So then members, let's take a look at the internal forces, the shear force, and the moment My. Okay, that looks quite good. At the bottom, we check the steel design. Yeah, we can see the message here. No effective lengths or boundary conditions are assigned. The stability design could not be performed. Yeah, we want to do only a cross-section design. Now, we assume the beam is supported in horizontal direction, and we do only a cross-section design. So that's why we go to the design ratios on members. You can see the two checks, the section-proof shear and Z-axis, and bending about Y-axis. Okay. So then you can double-click on such a line, or you can open the details with that button here. I check the button. So, and then you can see all the equations from the standard, also for the shear design check ratio or design. So, and you can see the section classification. It's class 1. That's why a plastic design, you can see that here, is possible. Plastic design also for the section-proof bending about Y-axis. Okay. And you can also print such equations with the hint where you can find it in the standard. With that button, print to the printer or to PDF or to the printout report. Students request for a detailed presentation of the proofs, and that's possible. Okay, class 1, plastic design. So now we want to an elastic design, voluntary in that case, because we have got class 1 here. So, and I would like to show where you can change the design. Here in the navigator data under steel design, you can see the ultimate configuration. Then you can double click on it, and you can check elastic design also for class 1 and 2 sections. The elastic design is possible for all cross-section classes. And we have got class 1, but we want to do an elastic design, voluntary in that case. Okay. So, and we run the calculation again. Now we should get a higher design ratio. You can see the design ratio is higher because, it's more safety because we did an elastic design. Just double click on it. Where you can see our formulas and you can see elastic design. Okay. So we have now learned how to carry out a cross-section check and how to take the elastic or plastic design into account. At first we did the plastic design, then the elastic design, as I mentioned, voluntary. And in addition, we now know how to display the design formulas and compare them with our own manual calculation. So let me start the last poll for today. So the question is, the elastic method applies to all cross-section shapes and can therefore always be used. Just check the right answer. Now remember that we did at first a plastic design and then we did an elastic design voluntary. Okay, then I will close the poll. Yeah, most of you checked the right button or give the right answer. All, the design can always be as or with the method elastic. Okay, let me go back to the slide. Yeah, you can see elastic is always possible, but for cross-section classes 1 and 2, you can do or consider the plastic cross-section resistance if you want. Yeah? But elastic is possible for all. So then we turn to the next topic: effects of deformed geometry of the structure. And in the first training course, Introduction to Member Design, it was learned how the results can differ between the calculation according to the first order theory and the second order theory. Geometrical linear analysis, it's equilibrium formation of the undeformed system, and the second order analysis is the equilibrium formation on the deformed system. In the example, you can see it on the right side. In the example of the cantilever column, this effect can be seen very well on the basis of a slender, slender on the left side and the compact cross section. In the case of the slender column, the increase in the bending moment at the foot point is much larger than the case, or in the case of the compact column, if one calculates according to second order theory. And for steel columns, you can see the criterion on the left side here. There's a value that defines when a structure should be calculated geometrically linear or according to the second order analysis. If the critical load factor alpha crit is less than 10, then the system must be calculated according to the second order analysis. Yeah, you can see if it's larger than 10, you can do a geometrical linear analysis, and it's smaller than 10, you have to do a second order analysis. Yeah, and 15 is the value for plastic global analysis. So then, equivalent geometric imperfections. Imperfections are also closely related to this topic. Here we have the imperfections in Eurocode 3. Yeah, and where these are generally grouped together as equivalent geometric imperfections. Now, maybe at first, what are imperfections anyway? Imperfections are production-related deviations in the model geometry and the material properties. On the one hand, there can be real misalignments in classic hull constructions or tolerances in production, especially when rolled sections are used. So what is also neat, or what I only also need to mention, yeah, and on the left side of the graphic, you can see the initial sway, global imperfection, that can be applied to the structure. And if individual components are to be examined more closely, there are local equivalent imperfections, for example, over an initial bow imperfection. This depends on the selected profile, the yield point, the buckling curves, and the proof method. These two variants are possibility of the equivalent geometric imperfections. Another alternative is the pre-deformation, which can be calculated with the help of stability analysis. But usually you use these two imperfections here. So then the next slide, stability analysis. Yeah, when designing an RFEM, 3 different stability analyses are carried out. On the left side, you can see the classic flexural buckling as a lateral deflection. Then the torsional buckling in pure tension, and the lateral torsional buckling as a combination of the two previous proofs. So then the next slide is also very important. There are the different methods for the stability analysis. The method A, you have to apply global and local imperfection, and you need to do, or to do a structure analysis according to the second order analysis. Method B, you have to assign global imperfections and a structure analysis according to second order analysis, but with the member length. So as you have to consider only the member length as buckling length. And then is the method C, structure analysis according to geometrical linear analysis on ideal structure. Now then you consider the effects of the second order theory by using the real buckling lengths. Yeah. Also here is mentioned structure component design on equivalent member according to section 6.3. So in the next example, we will first start with method C and then use method B. Now, there is an important sentence or important sentence mentioned in the explanations for Code 3. The structure component design can be carried out for flexural buckling with the internal force according to the geometrical linear analysis, which were determined on the ideal structure without the use of imperfections by considering the system buckling lengths. The moment increase according to the second order analysis and the effect of equivalent imperfections are already taken into account. But you have to consider, yeah, that's quite important for the design of lateral torsional buckling. The application of the second order analysis is also required with this method. Yeah, for example, for this column here, you could use the geometrical linear analysis, and for the horizontal beam, you usually want to do also the design for lateral torsional buckling, and then you need the second order analysis. Yeah, that's why usually you calculate this such or with this method and such structures, you use also the second order theory. Okay, that was quite hard stuff, I think. I turn to RFEM. I already prepared the model. Let me open it. I open the model, just a moment. I have to open the control center. So that's the prepared model. Or let me turn back to the PowerPoint slide, where also the model, the cross sections, you can see them in the image. That's the dimensions. There's one real frame here in the middle, then a connected horizontal beam and a column. There are hinges at the end of this horizontal beam, and the same is on the left side. So then 3 load cases: self-weight, snow, and wind. And the tasks for this example is apply imperfections and the stability analysis according to method B and C. And we start with method C, and then we apply imperfections and use method B. So let's turn back to RFEM. So that's the model. I go left at the bottom on the navigator display. So, and I check for the members. So the section name. Then you can see the different cross sections. Okay, so then the load, that's the self-weight load case, the snow load case. I divided the members without the, I created nodes here by dividing a member. Without dividing the member, I created only the nodes. The same as I did in the first example, that I can assign the loads to that members. So snow load case and then the wind load case. Wind pressure on the left side and wind suction on the right side. So then we turn left above to the base data. Again, the model 2D, plane stress. Then the add-ons. I will use the structure stability add-on and the steel design add-on. Standards, as in the first example, I use the Eurocode and the German national annex. Just select your national annex if you want, or the standard European annex. Okay. So then we will use the add-on structure stability. How to do that? I go or turn in the design situation. There's only one design situation, ultimate limit state. Steel design is already checked. We can through all the dialogues here quickly. Standard, the 3 load cases with the right action category, 3 actions, the design situation, and then the load combinations. And the design, also 3 load combinations, and the design situation contains all the 5 load combinations. Okay, and in the first step, we would like to do a geometrical linear analysis, and I open it. I can check this button here to edit it. So, and I would like to do a stability analysis. Okay. And I can calculate the design situation. So, yeah, when you take a look at the table, design situation number 1, here you can see the minimum critical load factor if you want to see it. And the results by done. We go to the stability analysis. You can also see the critical load factors, and we could see for the combination number 3, where's the minimum critical load factor, and you can see the results by node and results by member. And at the bottom, you can see the effective lengths. So let me increase the window. Yeah, for example, effective length factor 3 for this column. Yeah, almost 3 for this column. 1.73, I would say, for this column, and 1.73 for this column. Yeah, and in the first method, as the method C, we would like to apply the effective lengths. Now we would like to assign it to the different columns. So in the first step, I select the inner columns, double click on one. Now 2 are selected, and I switch to the design types, and I want to create the effective lengths. So then nodal supports and effective lengths, and I select 3 for the axis Y. Yeah, and that's all. Okay. Okay. So then I select these 2 with the with the control key. I can select both. You can see the plus here. Yeah, I hope you can see it. So, and then I double click on the member. The same for these columns, design types, effective lengths. Okay. And 1.73. Okay. So let's check if we did anything wrong. I go in the navigator display here at the bottom, then types for steel design, and I check member effective lengths. And you can see the different effective lengths, and you can compare it with the values in the table. I deselect the loads. And now you can see the values and can compare them. Okay, before we run the calculation, I go back to the design situation. So, and now I select the second order analysis. Yeah, as I mentioned before, to do the design for flexible buckling, you could apply the geometrical linear analysis, but we want also do a design for the lateral torsional buckling. Yeah. That's why we selected the second order theory. So, and to consider the lateral torsional buckling, I select the 3 horizontal beams. That was wrong, just a moment. I press the Control key, double click, yeah, now 5 to 7. Then, or let me do it another way. I double click only on the middle member, then design types. I would like to show you an interesting effect. So I go directly to the effective length. I create another effective length. So then I go to the nodal supports and effective length. So, and then I use that button here, select member or member set. The program detects the the intermediate nodes, and I would like to check or fix it in Y direction, in direction of the weak axis. So, and then I select all with the shift key, the intermediate nodes, and I consider eccentricity type. I would like to support or apply the supports at the upper flange. Just imagine we have got purlins in the horizontal direction, and those are at the top of the upper flange. That's why we would like to consider the support at the upper flange. Okay. And that looks quite okay. So for the outer horizontal beams, I select them. Did I get it? So double click on it, or I'm on them. Then design types, design type number 3. And the program detects automatically that there are only 3 intermediate nodes, and I considered this, or it consider the same horizontal supports. Although there are only 3 supports. The inner beam has got 4 supports. Now we have got only 3, but the program detects that automatically. So now we can run the steel design. Okay. So let's take a look at the section proofs. The maximum design ratio is 84%. Bending and buckling about the principal axis. Let's double click on that line, and you can see on the right side the formulas to hint where you can find them in the standard, and so on. Okay, I can leave the dialog. Yeah, this was the classic structured component method. Yeah, method C without imperfections, but effective member lengths. And now we want to examine the model using the approach of global imperfections and the structural component design, what means method B. Yeah, to do this, we change the buckling lengths or the buckling length coefficients of the support or of the supports back to 1. The buckling lengths of the columns, I mean. So I select them. So this one and this one. So then I change it back to 1. And for this one, also back to 1. Okay, yeah, the results are deleted. Yeah, and you can see the buckling length factor of 1 for all columns. So then above, yeah, you can see the imperfections, new member imperfection. I click on it. Imperfection case, yeah, is created automatically. So, and now we want to apply initial sway. You can also see initial bow, but we use method B. That's why we use the initial sway. You can see the different definition types and the different standards. We use the Eurocode 3. In imperfection direction, in the direction of the strong axis in our case, in Z direction. Okay, then we have to measure the structure height with that button here. So member height should be 8 meters. Okay, the program takes it over. The number of columns in one row is 4 in our case. And you can see the reduction factors and the initial sway are created automatically. That's all. We only have to turn to the design situation again. And we need to check if the imperfections are checked on. Yeah, we can edit the setting here. Yeah, it's checked on. Consider imperfection cases. That's quite important. Okay. So, and we can run the calculation. So we need to perform the steel design as well. So I increase the table here. So, and you can see the same design ratio. We can take a look. Okay, no, I did something wrong. I didn't select the imperfections. Where are the imperfections? Just a moment. Imperfections. I didn't assign them to the different members. I created the imperfection, but I didn't select all the 3 columns. Sorry, my mistake. We need to run the calculation again. I just wondered where we got exactly the same result. It's almost the same result now for method B. We had for method C for the 84%, and now we've got 86%. You can see the equations again here in that table. Okay, those are the two methods. We did at first method C and then method B. Yeah, that was all for this training. Now we are quite in time. Just wait for the email. You will get an email in the next days with the link to the recording and to the models and the PowerPoint slides. Maybe just one hint: when you leave the webinar or the online training, there is a small survey. It would be very nice when you score the online training. Just note that the worst score is 1 and the best score is 5. It's quite important to our quality management. You got a free online training, and it would be very nice if you take the time, only 1 minute, for some questions. It should be possible. Okay, I thank you for your attention. Thanks to Markus for answering the questions. I wish all a nice rest of the day, and bye-bye.